place is the blue. People to see time is precious. I look at my Cartier out of control. Just like my mind where I'm going. The women, the shorties know nothing but clothes. No stopping at my Pirelli's on. Unlike my jewelry that's always on. I know the storm is coming. My pockets keep telling me it's gonna shower. Call up my homies, it's on and popping the night cause it's meant to be ours. We keep a fadeaway shot cause we ballin' this platinum Patron every hour. Look, mama, I owe you just like the flowers. Girl, you the truth with all that goodies powers. My Benjamin Franklin's, a couple of grands, I got rubber bands, my paper planes making a dance. Get dirty all night, that's part of my. We building castles that's made out of. She's amazing, on fire blazing, hotter than Cajun. Girl, won't you move a little closer? Time to get paid, it's maximum wage. That body belong on the poster. I'm in the days, that bottom is waving at me like, damn it, I know you. You run the show like not a hoster. Tell me whatever, and I'll be your chauffeur.
Before we begin explaining how our device works, we'll first teach you the cross product between two vectors and the right-hand rule. Until now, we used to only have two axes, represented by x by I hat and y represented by j hat. But we learned at the beginning of the semester that the third axis can be introduced, which is the z axis, represented by k hat. This means that we can have three vectors in total. The multiplication between two vectors will always give the third vector that will be perpendicular to the other two vectors, and we also have to look at the direction of the two vectors to know the direction of the third vector. This is when the right-hand rule will come into play. You curl your fingers from the first vector of the equation to the second vector of the equation in the shortest way. The sum will give you the direction of the resulting vector. Let's do an example. Here we will multiply I cross product k. The answer will involve j since there are no other axes left, but the direction, according to the right-hand rule, is negative since it is going down. Another example, if we multiply I by negative j, using the cross product. The answer is plus k minus k since the sum is pointing out of the board, into the board. We must now try to apply all of this mathematical knowledge given to us by Tianren in the concept of magnetism. A magnetic force is created by and on moving charged particles in a magnetic field. Magnetic fields can be created in many different ways, such as by magnets and by wires with currents. A magnetic field vector can be represented by the B vector. Moving particles can be translated to electrical current. In an electrical current loop, a magnetic dipole can be generated. It is possible to find the magnitude and direction of this magnetic dipole using the right-hand rule shown before, as well as the formula shown in the image. When this dipole is placed in a magnetic field, it will try to align with the magnetic field. This will create a torque vector using the cross product shown. Objects will rotate around this torque vector, and with the direction of this torque vector, it is possible to find the direction of the spin by looking at the fingers in the right-hand rule, shown.
In our setup, 2-bar magnets supply a magnetic field, and a 9-volt battery supplies potential difference. The conventional current flows from a battery to one of the paper clips, to the coil of wire, to the other paper clip, and back to the battery.
Now that we have a basic understanding of magnetism, and we know somewhat how it works, let's really get into the explanation of how magnetism and our project works. So here, we look at the magnets that create a magnetic field, and the magnetic field lines are in blue and are shown with B. So the magnetic field lines are going up, positive Y. Now, let's try to find mu. So to find mu, we use the right-hand rules as explained by Tian. So we determine that the current is in this direction, so we take our right hand, curl the fingers in the direction of I, and our thumb points into the page. That's what shows the X. So that is equal to our magnetic dipole. So if our magnetic dipole is going into the page, and we have a magnetic field going up, so positive Y, we could use torque. So with the right-hand rule, our fingers point in the direction of mu, so into the page, and our fingers curl in the direction of the magnetic field, which leads our thumb of the axis of rotation of torque. So the coil will spin as shown. It will rotate along my thumb in this direction.
Fun fact, if the coil is placed as shown in the image above, there would be no rotation. That's because the magnetic dipole moment of the coil will already be aligned with the magnetic field caused by the magnet.